Lesson: Overfitting, Underfitting, and Generalization Issues. Overfitting and underfitting are critical issues in machine learning that significantly affect the generalization ability of models, especially in the context of AI model development risks within blockchain and AI risk management. Understanding these concepts is essential for professionals aiming to develop robust AI models that perform well on unseen data. Overfitting occurs when a model learns the training data too well, capturing noise and random fluctuations rather than the underlying pattern. This results in a model that performs exceptionally on training data, but poorly on new, unseen data. In contrast, underfitting happens when a model is too simple to capture the underlying trend of the data, resulting in poor performance on both training and test datasets. The balance between these two extremes is where optimal generalization occurs, allowing the model to perform well on both known and unknown data. Addressing overfitting and underfitting begins with selecting the appropriate complexity for the model. One tool for this is the bias variance trade-off framework, which helps to determine the ideal model complexity. High bias models are typically too simple and prone to underfitting, while high variance models are too complex and prone to overfitting. By analyzing the trade-off between bias and variance, practitioners can decide the optimal point for model complexity. Cross-validation techniques, such as k-fold cross-validation, are practical tools that can help assess how a model generalizes to an independent dataset. By partitioning the data into k subsets, training the model k times with a different subset reserved for validation each time, and averaging the results, one can gain insights into the model's performance stability and robustness. Regularization techniques are another powerful approach to combat overfitting. Methods such as lasso and ridge add a penalty to the loss function based on the magnitude of the coefficients. Lasso can shrink some coefficients to zero, effectively performing feature selection, while ridge penalizes large coefficients to prevent the model from fitting noise in the data. In practice, a combination of L1 and L2 regularization, known as elastic net, is often used to leverage the benefits of both techniques. These methods are particularly useful when dealing with high-dimensional data where the risk of overfitting is significant. Pause. Another practical tool is the use of ensemble methods, which combine multiple models to improve generalization. Techniques such as bagging and boosting are commonly used. Bagging, as implemented in random forests, reduces variance by training multiple models on different subsets of the data and averaging their predictions. Boosting, on the other hand, reduces bias by sequentially training models, each focusing on the errors of its predecessor, as seen in algorithms like AdaBoost and gradient boosting. These ensemble methods often lead to more robust models that generalize better to new data. Data augmentation is also a practical strategy to address overfitting, particularly in fields like computer vision, where data collection can be costly or difficult. By artificially inflating the size of the training dataset through transformations like rotation, scaling, and flipping, models can be exposed to a wider variety of scenarios, reducing their tendency to memorize the training data. In natural language processing, techniques such as synonym replacement or back translation can achieve similar augmentation effects. Feature selection is another critical aspect of preventing both overfitting and underfitting. By selecting only the most informative features, the model complexity can be reduced, which in turn reduces the chance of overfitting. Techniques such as recursive feature elimination and principal component analysis are commonly used. RFE recursively removes less important features based on model accuracy, while PCA transforms the feature space into a set of orthogonal components that capture the most variance. Hyperparameter tuning is an essential step in optimizing model performance and addressing overfitting and underfitting. Tools such as grid search and random search are traditional methods where different combinations of hyperparameters are tested to find the best performing model. More sophisticated approaches like Bayesian optimization can efficiently explore the hyperparameter space by building a probabilistic model of the objective function and using it to select the most promising hyperparameters. Practical examples of addressing overfitting and underfitting can be seen in real-world applications. For instance, in the financial sector, predicting stock prices requires models that generalize well to avoid significant financial losses. Techniques such as regularization and ensemble methods are used extensively to ensure models do not overfit historical data. Similarly, in healthcare, predictive models for disease diagnosis must generalize well to different patient populations. Data augmentation and feature selection are often employed to enhance model robustness. Statistics also highlight the importance of addressing these issues. Studies have shown that models with high variance error, indicative of overfitting, can lead to significant inaccuracies in forecasting and prediction tasks. For example, a study by data.Addressing demonstrated that ensemble methods could reduce test error rates by 25% compared to single models, underscoring the effectiveness of these techniques in mitigating overfitting. Continuous monitoring and evaluation are crucial in maintaining model performance. Once deployed, models can drift due to changes in the underlying data distribution, a phenomenon known as concept drift. Implementing mechanisms for regular model evaluation and retraining ensures that models remain accurate and relevant over time. Techniques such as drift detection algorithms can be employed to trigger model updates when significant changes in data patterns are detected. In conclusion, understanding and addressing overfitting, underfitting, and generalization issues are paramount for AI model development, particularly in the realm of blockchain and AI risk management. By leveraging practical tools and frameworks such as regularization, ensemble methods, data augmentation, feature selection, and hyperparameter tuning, professionals can develop models that are robust and generalize well to new data. Real-world examples and statistics reinforce the importance of these strategies, providing actionable insights for tackling these challenges. Continuous evaluation and adaptation further ensure long-term model performance, supporting the development of reliable and effective AI systems.